Okay, two quick disclaimers before I start this video. One, my dog is here and he may bark really loud at any moment, and that'll keep you on your toes. Two, my stylus is broken, so I'm going to be drawing with my index finger, so it's going to be messier than usual. Okay, but so I first wanted to look at the improper integral from 1 to infinity of 1 over x dx. It may help with interpreting these integrals if you have some kind of, if you can attach a physical meaning to it. So here I have the graph of 1 over x in the first quadrant. The integral, let's see, here we go, integral from 1 to infinity of 1 over x dx. We could think of that as the area under the curve, y equals 1 over x, as x goes from 1 to infinity out this way. So it's the, sorry, I'm distracted by that red line. That's insignificant. It's not supposed to be there. Oh, you guys can't see it, can you? That's the bottom of the video window. Now I get it. Okay, but anyway, so that integral, you can think of it as representing this area. Whoopsie. Okay, I'm still recording. Okay. That's an unbounded region. So we can't really, if it's an infinite region, we can't really talk about area of that region. But let's see if I can switch colors. What we could do is set up a right-hand boundary over here. Let's call it t, and then take the limit as t approaches infinity. So that way, let me change the integral up here. So let's say we think of it as the integral from 1 to t of, it takes a second to change colors in this application, of this integral. So it's the area from 1 to t, and then we take the limit on the outside, oops, okay, limit as t approaches infinity. So if you picture that, say we evaluate that limit as a table, and we actually evaluate it as area. So you'd be finding the area under this curve going from 1 to t, and then you let this right-hand boundary slide off toward infinity. And so in that table, you may see behavior like the area is 1, and then it's 2, and then it's 3, and it's just increasing without bound. In that case, we say the improper integral diverges. And I'll show you how we actually compute that, how we write that out in a minute. If in your table, if you imagine that your areas as t slides out towards infinity, maybe your area has this behavior where it's 1, and then it's 2, and then it's 2.5, and then it's 2.3, and then it's 2.1. So that if it seems to be zeroing in on, like in this case, 2, the way I'm describing it, then we would say that the integral converges to 2, because the area seems to be approaching a finite value of, say, 2. So those are the two things that can happen with these improper integrals. Now, as far as how we actually evaluate it, first thing is to set it up as a limit. So you replace your infinite limit of integration here with a dummy variable, let's say t, and then on the outside of that integral, you allow t to approach infinity. So now, from here, the way we evaluate it is we would find the antiderivative of the integrand here, the 1 over x, and then substitute the endpoints. So it's just like you would evaluate any other definite integral. It's just that in the last step, and not until the very last step, you'll take the limit as t approaches infinity of whatever expression you end up with. So in this case, we would want the antiderivative of 1 over x, which is natural log of x. So this becomes the limit, like I said, I'm writing with my finger, let's see, of, okay, so the antiderivative of ln of 1 over x is ln of x as x goes from 1 to t. Now you substitute your limits of integration. So this is the limit as t approaches infinity of, substitute the upper limit of integration minus substitute the lower limit of integration. And so this is equal to the limit as t approaches infinity of natural log of t minus natural log of 1 is 0. Okay, so now in evaluating that limit for natural log of t, if you can picture, let me write this in a different color. The graph of 1 over x, or 1 over x, ln of x, sorry. The graph of ln of x looks like this. So as t approaches infinity, the value of natural log of x approaches infinity. It's an increasing function. So this limit right here is infinity. Let's switch back to okay, minus 0, so it's equal to infinity. So when you get a limit like infinity, that's saying that if we had created some table of the area under this curve here, the values would have just been increasing without bound. They weren't like leveling off at some finite value. So when you get a limit like infinity or a limit that does not exist, we say that the improper integral, so this integral from 1 to infinity of 1 over x dx diverges.